we are going to start module 4 of chapter 5. In this module, we shall discuss principle of least action. In the previous modules, we have discussed Hamilton's principle and extended it to obtain extended Hamilton's principle. There we have used only Kronecker delta variation, but to establish the principle of least action, we need another type of variation, which is the triangular delta variation. In this module, we shall discuss triangular delta variation, its difference with Kronecker delta variation, and with the help of these we shall establish principle of least action. In this module, we shall discuss triangular delta variation, its relation with Kronecker delta variation, and using these principle of least action will be established. Now, triangular delta variation and its relation with Kronecker delta variation. In case of Hamilton's principle, the varied paths and the actual path share the same terminal points, that is T0 and T1, which are fixed in such a way that delta q at T0 equal to 0 as well as delta q at T1 equal to 0. Many physical situations arise where the boundaries may vary. For such situations, we have to consider another type of variation. We introduce a more general type of variation, which is triangular delta variation of the path for the dynamical system, that is one in which changes in time are also allowed. Please remember that changes in time in Kronecker delta variation is not allowed. For triangular delta variation, we assume that time and position coordinates are variable along the path. Number 2, time also varies at the end points of the path. Number 3, but the position coordinates are fixed at the end points. From the figure given in next slide, you can visualize that the configuration space in which capital A0 represents the actual path and capital B0 is the varied path of a dynamical system. Point P on the actual path represents the point with coordinates qi through which the dynamical system passes at time t. At the same time, the system, you can visualize the figure 5.2, where two paths are traced. Lower path is the varied path, upper path is the actual path. In the varied path, t plus delta T0 is the initial time, whereas t plus delta T1 is the final time. Here delta is the triangular delta, whereas in the actual path the initial time is T0, final time is T1. At varied path, capital Q is the position of the particle at time t, having coordinates qi plus delta qi, where p corresponds the position at the same time on the actual path having coordinate qi, where capital R, whose coordinate is qi plus triangular delta qi, is the position of the particle at the varied path at time t plus triangular delta t. A0 denote the actual path, B0 denote the varied path. The particle passes through the point capital Q with coordinates small qi plus delta qi on the varied path capital B0. At the latter time t plus triangular delta t, the system passes through the point capital R with coordinates qi plus triangular delta qi on the varied path. Then from the figure it is clear that triangular delta qi equal to Kronecker delta qi plus qi dot into triangular delta t. This is the relation between the triangular delta and Kronecker delta variations. Let small f equal to small f function of generalized coordinates q1, q2 up to qn, generalized velocities q1 dot, q2 dot up to qn dot and time t. Now we have triangular delta qi equal to Kronecker delta qi plus qi dot into triangular delta t. Let f is a function which depends on generalized coordinates q1, q2 up to qn, generalized velocities q1 dot, q2 dot up to qn dot and time t. Let us calculate triangular delta f, that is change of small f. Triangular delta f can be written as summation over I varying from 1 to small n, del del qi operated on small f into triangular delta qi plus del del qi dot operated on small f into triangular delta qi dot plus del del t operated on small f into triangular delta t. Please note that we are considering the change triangular delta of f. As f depends on qi and qi dot and time t, we get this result using the chain rule. Now let us substitute the expression for triangular delta qi from the result already obtained, and we get the next line, that is triangular delta f equal to summation over I del del qi of f into Kronecker delta qi plus qi dot into triangular delta t plus del del qi dot of f into Kronecker delta qi dot plus qi double dot into triangular delta t. Last term is written as it is. Now writing the similar terms within the first bracket and here within the third bracket, we get the next line. Now the terms within the first bracket can be written as Kronecker delta f, whereas the terms written within the third bracket can be written as ddt of small f into delta t. So we finally have triangular delta f equal to Kronecker delta f plus ddt of small f into triangular delta t. Thus we can write the operator as triangular delta equal to Kronecker delta plus triangular delta t into ddt. Note, we shall consider those varied paths for which generalized velocity qi dot are such that if the Hamiltonian capital H is conserved for the actual path, it is also conserved for the varied paths. Number 2, the variation triangular delta qi are assumed to be 0 at the endpoints. Number 3, capital A equal to integration T0 to T1 summation over I equal to 1 to n pi qi dot dt is the action integral, where small pi is the generalized momenta, qi dot is the generalized velocity. Now, we shall discuss principle of least action. The principle of least action states that the integration T0 to T1 summation over I equal to 1 to n pi into qi dot dt is stationary for motion in actual path between two configurations of the system as compared to the motions along the neighboring paths between the same two configurations, provided the Hamiltonian H has the same constant values in the varied path as well as in the actual path. Here pi is the generalized momenta, whereas qi dot is the generalized velocity. Now, we shall verify the principle of least action. Let capital A be the value of the integration T0 to T1 summation over I equal to 1 to n pi qi dot dt, pi being the generalized momenta, qi dot being the generalized velocity, when taken along the actual path between the times T0 and T1, that is capital A equal to integration T0 to T1 summation over I equal to 1 to n pi qi dot dt. Let capital A dash be the value of the same integral when taken along the varied path between the time limits T0 plus triangular delta T0 and T1 plus triangular delta T1, that is A dash equals to integration T0 plus triangular delta T0 to T1 plus triangular delta T1 summation over I equal to 1 to n pi qi dot its value 1 dt, where summation over I equal to 1 to n pi qi dot 1 denotes the value of summation I equal to 1 to n pi qi dot at the moment t in the varied path, that is summation I equal to 1 to n pi qi dot 1 equal to summation I equal to 1 to n pi qi dot plus Kronecker delta of summation I equal to 1 to n pi qi dot. Now, triangular delta A equal to integration T0 plus triangular delta T0 to T1 plus triangular delta T1 summation I equal to 1 to n pi qi dot 1 dt minus integration T0 to T1 summation over I equal to 1 to n pi qi dot dt. But Hamiltonian H is given by capital H equal to summation over I equal to 1 to n pi qi dot minus L, or we have summation I equal to 1 to n pi qi dot equal to capital H plus capital L. So far we have discussed about the triangular delta variation and conical delta variation, already established their relation. Now using their relation we shall prove an important variational principle, which is the principle of least action. Now triangular delta A is equal to integration T0 plus triangular delta T0 to T1 plus triangular delta T1 of H plus L suffix 1 dt minus integration T0 to T1 H plus L into dt. This can be written as integration T0 plus triangular delta T0 to T1 plus delta T1 H into dt. Since H has the same value in actual path as well as varied path, plus integration T0 plus triangular delta T0 to T1 plus triangular delta T1 L1 into dt minus integration T0 to T1 capital H into dt minus integration T0 to T1 L into dt. In this line we have written the terms from the above line in a explicit manner using the fact that H equal to H1. Thus, triangular delta A can be written as H integration T0 plus triangular delta T0 to T1 plus triangular delta T1 dt. Since H is independent of the integration, so we can write the first term in this way, plus integration T0 plus triangular delta T0 to T1 plus triangular delta T1 L1 dt minus H integration T0 to T1 dt minus integration T0 to T1 L dt. On integration, first term and third term can be combined, and we have written the result in the first term of the next line, and the other terms have been written in a explicit manner using the property of definite integrals. Now, the first term of the previous line can be written as capital H into triangular delta T taken at T0 to T1 plus first term and last term can be combined in the next term as integration T0 to T1 L1 minus L into dt. Third and fourth terms have been written as it is in the next line. Now, the first term is written as it is, that is H into triangular delta T at T0 to T1 plus from the second term of the previous line we get capital L1 minus L is conical delta L, which has been written in the second term of the final line of this slide. Third and fourth integral can be combined as L1 taken at T1 into triangular delta T1 minus L1 taken at T0 into triangular delta T0. Therefore, triangular delta A equal to capital H into triangular delta T at T0 to T1 plus integration T0 to T1 Konekat delta L dt plus L1 at T into triangular delta T taken at T0 to T1. Again L1 T into triangular delta T equal to L plus Konekat delta L into triangular delta T, which can be approximated as L into triangular delta T, since the product of Konekat delta N and triangular delta T are very small, and so we have neglected this one. But Lagrangian is a function of generalized coordinate qi, generalized velocity qi dot and t. So, the variation of Lagrangian gives Konekat delta L equal to summation I equal to 1 to n del L del qi Konekat delta qi plus summation over I equal to 1 to n del L del qi dot Konekat delta qi dot equal to summation over I equal to 1 to n del L del qi delta qi plus del L del qi dot delta qi dot. Therefore, integration T0 to T1 Konekat delta L dt equal to integration T0 to T1 summation over I del L del qi Konekat delta qi plus del L del qi dot Konekat delta dqi dt into dt equal to integration T0 to T1 summation over I del L del qi delta qi plus del L del qi dot ddt of delta qi dt. Here we have used that ddt and delta variation can be interchanged. Therefore, integration T0 to T1 delta L dt equal to integration T0 to T1 summation over I pi dot Konekat delta qi plus pi ddt of Konekat delta qi into dt. Since the last integral holds for actual motion, for which we have from Lagrange's equations of motion ddt of del L del qi dot minus del L del qi equal to 0 for I equal to 1, 2 up to n, or ddt of pi equal to del L del qi, that is pi dot equal to del L del qi, I varying from 1, 2 up to n. Therefore, integration T0 to T1 Konekat delta L dt equal to integration T0 to T1 ddt of summation over I pi Konekat delta qi dt equal to summation over I pi Konekat delta qi at T0 to T1. Therefore, substituting 5.23 and 5.24 in 5.22, we get triangular delta A equal to capital H plus L into triangular delta T at T0 to T1 plus summation over I pi into Konekat delta qi taken at T0 to T1. But triangular delta qi equal to Konekat delta qi plus qi dot into triangular delta T, or Konekat delta qi equal to triangular delta qi minus qi dot into triangular delta T. Using this in equation 5.25, we have triangular delta A equal to capital H plus capital L into triangular delta T taken at T0 to T1 plus summation over I pi into triangular delta qi minus qi dot into triangular delta T taken at T0 to T1 equal to capital H plus capital L into triangular delta T taken at T0 to T1 minus summation over I Pi into Qi dot into triangular delta T taken at T0 to T1. Combining these three terms, we have triangular delta A equal to capital H plus capital L minus summation over I Pi Qi dot into triangular delta T taken at T0 to T1 equal to 0. Since triangular delta Qi equal to 0 at T0 and T1 and capital H equal to summation over I Pi Qi dot minus L. Thus, the action integral capital A is stationary along the actual path as compared to the neighboring paths, provided all motions considered are subject to the same conservation of energy. Remarks: integration T0 to T1 summation over I Pi Qi dot dt is generally called Hamilton's characteristic function. In a conservative system, integration T0 to T1 summation over I Pi Qi dot dt equal to integration T0 to T1 capital H plus capital L dt equal to integration T0 to T1 capital T plus capital V plus capital T minus capital V dt, since H equal to capital T plus capital V, whereas L is equal to capital T minus capital V. Therefore, we have integration T0 to T1 summation over I Pi Qi dot dt equal to integration T0 to T1 2 into capital T dt. From the principle of least action, we already have from equation 5.26 triangular delta A equal to 0, that is triangular delta of integration T0 to T1 summation over I equal to 1 to n Pi into Qi dot dt equal to 0. From 5.27 and 5.28 we have triangular delta integration T0 to T1 2 into capital T dt equal to 0. This is valid only in conservative dynamical system and is known as Lagrange's principle of least action. 3. In Hamilton's principle, the times T0 and T1 are prescribed in a configuration, that is the time interval is prescribed, but in principles of least action the total energy between the endpoints are prescribed. The endpoints are fixed in both the Hamilton's principle and in principle of least action. In our previous module, we have discussed the detail about Hamilton's principle and used it to obtain Lagrange's equations of motion and Hamilton's equations of motion. Hamilton's principle is derived using the Hamiltonian function, but in this module we have derived the principle of least action, which is another variational principle with the help of Hamilton's characteristic function. In establishing this principle, we have used two types of variation, which are triangular delta variation and conical delta variation.